Today we will go for chapter 1, multiple life functions. So in actual math 1, we already cover for one life. So the actual present value for basic benefits are derived by applying the concepts and techniques developed in SQQM 2073, but the difference is for this time we have two lives. So models built on the assumption that the two future lifetime random variables are independent constitute most of the chapter. A useful abstraction in the theory of life contingencies, particularly as it is applied to several lives, is that of status, which there are definitions of survival and failure. So the status have two kind of status, whether survive or failure. So failure is referring to death. Okay, so a single life each X, like in the actual math 1, define a status that survive while X lives. So this X is referring to an individual each for a single life. Thus, the random variable Tx used in chapter 1 to denote the future lifetime of X can be interpreted as the period of survival of the status and also the time until failure of the status. So the Tx, for example, this is the timeline. So X is the current age for an individual. So the big X is for the death or for the failure time. So this period we call it as the future lifetime of Tx. So we denote as Tx. A term certain n defines a status surviving for exactly n years and then failing. So the notation is like this. More complex statuses can be defined in terms of several lives in various ways. Survival can mean that all members survive, or alternatively that at least one member survives. So there are two kinds of survival, whether all members survive or at least one member survives. After a status and its survival have been defined, we can apply the definition to develop models for annuities and insurance. So do you still remember annuities? Small a, and insurance is big A. An annuity is payable as long as the status survive. And then insurance also can be restricted, so they are payable only if the individual die in a specific order. So that's the difference between annuity and insurance. Annuity is about surviving. Insurance is about dying. Okay, the first type of multiple life function. So the joint life status, or we call it as JLS. So we consider two life, X and Y. So before this single life, we only use X. And so now we have two variables, two life, X and Y. So the JLS for X and Y survive as long as both X and Y are alive and fails upon the first death. So if we draw the timeline from 0 to T, meaning for T is for the time of failure. So for the first death of X or Y, JLS status fail. So TXY is a random variable representing the future lifetime of JLS status for both X and Y. So recall, before this, we learned in actual math 1, Tx is a random variable representing the future lifetime for X as well as for Y. So for joint life status, TXY is the future lifetime of the JL status is the minimum of future lifetime for X, TX, and TY. So after the first death, because after the first death, it considered failed. So we take the minimum time of failure. So, and we consider that TX and TY are independent because the event of death for each individual is different. So it is independent. Okay, so next slide, we go to distribution function of TXY, or for the future lifetime for X and Y. So remember distribution function. So the DF is the big F. So distribution function of TXY is F, and in the bracket is TXY. So since, remember in Natural Math 1, big F is about death, the probability for death or the failure. So probability for death or failure. So if we write down in terms of probability, it is before or equal to T, because T is the time of failure. So we take the minimum because the first death is considered as fail, and then we got this one. So after and this is N. Remember N in statistic we use this symbol, and then after we convert it in terms of actuarial notation, we get 1 minus TPX times TPY, which is probability of survive of X and Y, and then we get TQX for different distribution function of TXY, TX and Y. So because we're talking about death or failure, so in actual notation we use TQX before this. Since there are two lives now, so it becomes TQXY. Okay, now look at the note. Okay, TPXY is equal to TPX times TPY. Why? Because we have N here. Because we have N here. Remember N in statistic, this one is N. We have to multiply A and B. So this is, we use multiplication. So for TQXY, probability of death is 1 minus TPXY. And then after we expand the equation, and the final one we get TQX plus TQY minus TQX times TQY. So the first equation for TPXY is TPX times TPY. If you want to convert it into TQX term, so you use this one, TQX plus TQY minus TQX times TQY. Okay, next. So now we go to PDF. So PDF. So PDF, if you write down in notation, it is small f. So the concept is same as in Actual Math 1. So the difference is only there are two lives in this chapter. So there are typo in your notes. Please correct. You have to delete the d over dt in this line. And then you also have to add TPXY in front of the bracket. Okay, so in the previous slide, we derive density function of txy. So when we want to convert it in terms of PDF, as you know, we have to differentiate the distribution function. So after we differentiate, the it becomes tpxy times mu x plus t plus mu y plus t. Okay, you can check the side note where differentiation of tpx equal to negative tpx mu x plus t. So we already covered this one in previous course. Okay, let's move to next slide. Force of failure of TLS of xy at time t. So remember at last course, we have force of mortality. So this time is still the same force of failure. We use mu xy t. So the formula for mu is PDF over 1 minus a big F dxy. So we get mu x plus t plus mu y plus t. Therefore, PDF is equal to tpxy times mu xy t. Therefore, PDF is equal to tpxy mu xy t. Okay, we go to example 1. Show that the probability of JLS of xy will fail between time t and t plus u given as tpxy minus t plus u pxy. So the fail between time t and t plus u. So the probability fail between this time with condition that both individuals are survive until time t. Okay, now we use probability from times t to t plus u, and then we convert it into actual notation and we get tpx times tpy minus t plus upx times t plus upy. And then we also can write down and then after we simplify, we can use this equation tpxy minus t plus upxy. We also can write this situation in terms of probability of death or qxy. So we use this notation. So remember in last course we learned this as the deferment. So which with condition of that individual must survive until time t. Okay, we move to another slide. So we integrate the PDF. This is the PDF. PDF is tpxy mxy t. So this equation is very important. You have to remember. So integration of the PDF is equal to 1 from upper bound is 0 and the lower bound is 0 until the infinity. So it is equal to 1. So you have to remember this equation. So in order to calculate the probability of death and probability of survive. So TQXY and TPXY. So for TQXY, the upper bound is until T, because the time of failure is at time T. And the probability, if you write down in terms of probability, the TQXY is less than, it happens before T or equal to T. And for probability of survive, T until infinity, because in terms of probability is greater than T. Alright, example 2. Given the De Morph's law with omega equal to 100, find probability of survive for individual with age 20 and 30 until 10 years. So if you write down in terms of numbers here, you have to put the double dot here. So this one is for X and this one for Y in terms of age. So then is the T. So remember for JLS, TPXY is equal to TPX times TPY. So for P2030 is equal to 10 P20 times 10 P30. Okay, since the information that you have is omega equal to 100, so we can use a survival function. So Sx plus T over Sx. So and then you can solve S40 over S20 equal to 60 over 80, and we simplify and we get 3 over 4. So remember, this is probability, so the value must be in range of 0 until 1. Alright, so we go to example 3. If mu x is equal to 0.06 for all x and mu y is equal to 0.8 for all y, find probability of death for x and y for t years. So mu is force of failure or force of mortality. So now we find probability of death for QXY. So we are given in terms of force of failure. So we can use integration. Remember, for probability of death, 0 until t. So t is equal to 10. So TPX times TPY times mu x plus t plus mu y plus t dt. Then you can solve. So you are given mu x, so we can change dpx into in term of e negative mu x plus t times e negative mu y plus t times mu x plus mu y, because mu x is equal for all x and mu y also is equal for all y. And then we can plug in the mu values into the equation. So we got constant value 0.14. We take out the constant value. And now we integrate the exponential. So we get 0.14 and we get 0.7534. Okay, now we go to second type of multiply function. So the second one is the last survivor status, or the short form is LSS. Okay, the last survivor status, the notation is XY with the bar. So it differs with JLS. JLS we have the notation XY without the bar, and for the last survivor status, XY with the bar. So you have to remember the notation. So LSS or XY survive as long as at least one of X and Y survive and fails upon the last death. So as long as there is one survivor, then it's still active. The status is still active until both death. So the status fails. So the last death of X and Y. So the future lifetime of the LSS is TXY with the bar. Now we go to the distribution function of TXY. So the big F, the DF, same as the JLs. So the big F is still same as JLS. However, the difference is we take the maximum future lifetime of both X and Y. So in JLS, we take the minimum future of lifetime. So the difference is, if we write down in terms of the probability of death, it is TQX times TQY. So the first equation And then if you want to write down in terms of TPX, it becomes 1 minus TPXY. Alright, so now we go to PDF. So the PDF, the small f, is differentiation of the TF. After we expand the equation, and finally we get this one. It's a very long equation. TPX times mu x plus t plus TPY times mu y plus t minus TPXY times both mu x plus t plus mu y plus t. So now we try example 3. Show that the probability of the LSS will fail between time t and t plus k is given by the probability of death qxy to t plus k is equal to qxy to t. So if we draw the timeline, so the probability that we want to find is from t to t plus k. Probability of fail. So it is maximum of future lifetime of Tx and Ty greater than T minus T plus U is equal to 1 minus plus u. So we simplify and then we get negative dqxy. Since it is LSS, we have to put the bar plus d plus u qxy. Therefore, we can prove that dqxy is equal to d plus u kxy.